we now know how to add vectors, and the main idea behind adding vectors was that given two vectors, vector A and vector B, you would align the tail of vector B with the head of vector A to get some sort of like a continuous path between these two vectors, and then you would take from the tail of A till the head of B, you would form a vector, and that would be the sum of the two vectors. And based on this, let's try adding A to itself. Let's consider a special case of this. So what happens if you add A to itself? So basically, now you have two copies of the vector. Let me do that, one in blue and one in white. And so the one in white and the one in blue are the same. They have the same magnitude, they have the same direction. And when you add them, when you take this tail and you align it with this head, what you basically do is you keep the same direction. You keep the same direction since you're just progressing in the already defined direction, and you get 2 times the magnitude. So now if the starting magnitude, if the magnitude of this blue vector and this white vector alone individually was small a, then the magnitude of this entire vector right here would be twice that. It will be 2 times a, or 2a, and the direction would remain the same. And in general, you could continue that as for as many vectors as you want. And a nice way to interpret would be that if you wanted to run 3 kilometers west and 3, let's take 2, if you wanted to run 3 kilometers west and 2 kilometers north, and you wanted to repeat that again and again, so you run 3 kilometers west and 2 kilometers north, something like that, and then you do the same thing again and again. So this path would rather continue, and instead of that, what you could have done, instead of taking 2 different vectors, what you would have said, we are running 6 kilometers west if you do the same thing 2 times, and 4 kilometers north. And while this will take some time to build this idea when we come to resolving vectors, and that's something we will come to in later videos, for now let's just consider the fact that we can add a vector to itself. And in general, if you multiply a scalar lambda number, a scalar lambda, with a vector a, you get a vector lambda times a vector, which has the same direction, as a, but has lambda times the magnitude. So if you started out with, let's say, a vector of magnitude 5 units, if you multiply that vector by 10, the resulting vector has a magnitude of 50. And while this holds true, this is sort of intuitive. When you use positive scalars, you could do the same thing for negative scalars as well. So for negative scalars, what happens then? Now, this by the way is when lambda is positive, then you get this. But then if you have a negative lambda, if you have a negative scalar, what happens? So then what was your original vector? Let's say this was your original vector with some magnitude a, small a, and direction in some random area where you want it to be. And let's say you multiply it by -1. So negative of vector a. What does that mean? So if you take it sort of in a physical sense, now going 3 meters right and 3 meters up becomes, if you do the negative of that, it becomes 3 meters left and 3 meters down. 3 meters down. So the negative, really, what it does, when you multiply a vector by -1, it really just inverts the direction, and that makes sense. Instead of going in one path, right, like in this green path, you instead go in the opposite path. So something like this. And this vector now is negative of A, negative of vector A, it still has the same magnitude. Remember this vector right here still has the same magnitude, but the direction is opposite. So in a sense, you could write the direction of negative A is equal to negative of direction of A. And now you can also build this argument not only for -1, but for any negative number you want. And by that you have formed the basis for scalar multiplication. Now you can multiply a scalar by a vector. And a really nice example for this in physics would be momentum. And momentum, to be really rough, is a measure of how hard something will hit you. So if something has a higher mass, and so if something with mass 3 kilograms and velocity 1 meters per second to the right, and if you have another thing with mass 2 kilograms and velocity again 1 meters per second to the right, it's more likely that this one will hurt you more than this 2 kilogram thing. And momentum, which is usually denoted by the letter P, momentum is actually a vector, and it's equal to mass times the velocity. And so that means as mass goes up, momentum goes up as well. And as the magnitude of velocity goes up, the magnitude of momentum still goes up. And the direction of momentum, the direction of this vector P, is actually equal to the direction of the vector V, because m cannot be negative, the mass cannot be negative, so the direction is always momentum always lies in the direction of the vector at that instance. And when we have defined it for negative scalars as well as positive scalars, only one number remains, and that is the number 0. And so if you multiply 0 by a vector B, let's say, you get nothing. You get the 0 vector. And the 0 vector it doesn't actually signify something, but it sort of gives you an idea of how a vector of doing nothing happens. So if you for a mathematical need, you could say when you add vector A to the negative of vector A, what do you get? Well, in that case, you get the vector 0. Why? You get the 0 vector. Why? Because then what you're doing is you go in a certain path, and through the same path you just return. And you just return to the same path in the opposite direction, and you just end up where you started. So really there is no change in the position from which you started. The initial and the final positions are the same, and the 0 vector is just that. It's just so shows that nothing really has changed. And also, given the fact that you now know what negative scalar multiplication is, we can go on to learn a bit about addition, induced subtraction. So in a way, when you say vector A minus vector B, what you're actually meaning to say is vector A plus minus vector B. And that means that if given two vectors A and B, so if this is vector A and vector B lies here, then if you want to subtract these two vectors, the first thing that you would do is multiply this vector B by -1. And by doing so, you get this part. You get -b. So let's do that. Let's invert -b. We just need to change its direction. So you get the vector -b. And now you can shift this -b vector so that it aligns with the head of A, sort of to get the same idea as you had in addition. You're just doing the same. Now you basically now have two vectors. One is vector A and the other is vector -b, and you have to align them. You just have to add them now. So even forget that there is a negative sign. Let's just consider this to be vector C. So now you need to add vector A and vector C. So you just do that. You just align the tail of C with the head of A, and now you join the tail of A and the head of C, and the resultant that you get in that process is actually vector A plus vector C, which is equal to vector A plus negative of vector B, and which is the same as vector A minus vector B. So sort of by doing scalar multiplication, you're able to define the addition of one vector to itself, sort of the analog of multiplication, but then there is also vector multiplication, so we will call it scalar multiplication for now. And then we also use the concept of negative scalar multiplication to actually define vector subtraction. And we can get more practice on vector addition and subtraction, and we also looked at what the momentum means, just a brief idea. And also remember what the zero vector is. It's nothing, just it's nothing. It's actually just nothing. It's just no change in the position in the coordinate axis, in the coordinate plane. See you in the next video.